In section 3.5, we're encountering another kind of function. We've seen these functions before. We saw them back in chapter P, a long time ago now. They're related to polynomial functions because rational functions are simply a ratio, right, like fraction, where you have a polynomial on top and a polynomial on bottom. Okay, so it's much related to what we saw before, but obviously because of that denominator issue, graphs do look different. The first two problems, I'm going to switch this to in a minute. I just want you to do your best to answer them. We've seen stuff like this before. May not be recently because it was like chapter P stuff. But see if you know the answer or how to answer them. If you don't freak out. We're going to do it together, I promise. We've got two functions. They are both rational equations. And you're supposed to state the domain. Let's chat. Domain. Is that x values or y values? X, good. X values. When we were working with polynomials, the domain is all real numbers. There's no problems. But when we start working with rational expressions, there is a potential problem when we're doing that. What's the potential problem that could come up? We can't have a denominator with a 0, right? I mean, the whole denominator itself can't be 0. So anything that would make the denominator 0 is a problem. So oftentimes domain is easier to answer the question of what can x not be, right, than what can x be. So on the first one, what can x not be? 2. And while it's perfectly fine to write that in sort of set notation, and we've talked about that before, it'll be more useful for us to think about it in terms of an interval because we're going to be graphing later in this section anyway. So if we think about what x can and can't be, this means that we can have all the values sort of starting at negative infinity, right, up to 2. And we put a parenthesis because we can't equal that value. And then we have a union, much like the last problem we did in section 3.4. And we pick back up with 2 again and continue on. I had a student this morning that asked me, are we always going to have parentheses as opposed to brackets on these? And I am not thinking of any case where you would use brackets because the whole point of parentheses is you're excluding values, right? You're not able to have specific values because of denominator issues. So you're going to see a lot of parentheses in this section when you're dealing with intervals. Okay, so taking a look at the second example, how is it different than the first? I need to factor it. Yeah, the denominator's got more going on. I don't just have a simple binomial that I set equal to 0 and solve. So I need to be able to factor. And while in reality the numerator on this one doesn't factor, even if it did, it won't matter. Because the denominator being 0, no matter what happens in the numerator, is a problem. Okay? So the denominator issue is the only issue we're going to address right now. We'll come back to the numerator a little bit later in our class discussion. But we need to figure out where this denominator equals 0, and factoring is a great way to do that. So how will the denominator here factor? And we almost saw we saw a very similar one to that in the last chapter section, right, 3.4. All right, so what are the things that x cannot equal on this one? -4 and +3. And if we're thinking in terms of an interval, that means we start with -infinity. And what is the first of those two values that we will come to? -4. And if you think in terms of a number line, some of us are more visual than others, and I do realize that. You're welcome to put things on a number line to be able to draw these. So this point right here is the problem, and so is this one. So as we're creating these parentheses, you've got something that's going to look like this from a number line perspective. So this is -infinity to -4. Be careful. Don't just jump over to the part where it goes to infinity. You still have a piece in the middle here, right? You can see it on the graph. What is the piece that comes next? -4 to 3. And then you have 3 to infinity. So here is the answer for the domain in terms of an interval notation for each of these. All right, moving on to something slightly different. We're going to come back to those two examples over the next couple of slides. We're taking a look at something called asymptotes. We haven't talked about asymptotes in this class, at least I haven't talked to you about them. Asymptotes, I'm going to give you my verbal description. An asymptote is a line you get really close to and don't touch. And the word don't is kind of fuzzy as well, because occasionally you actually do. You know, it's a super terrible definition. The one on the board is specifically for vertical asymptotes, and it's more precise. If a rational function is in lowest terms, we'll come back to that. Its vertical asymptote, or totes, if there's more than one, are the value or values for which the denominator equals 0. And there are equations. Asymptotes are equations. These equations say x equals some number. So what do you suppose this phrase lowest terms means? What would a function in lowest terms look like compared to something that's not? Yeah, it might need to be factored and simplified. Okay? Some functions very clearly don't. Some functions very clearly at least got to be checked out. So vertical asymptotes are so directly related to the concept of domain, it's almost freaky scary. If you've done one, you've almost pretty much done the other one. So let's go back to those two problems we had before, and we're going to find their vertical asymptotes. But they have to be in lowest terms, so we have to double check that on each one. On the first one, is it in lowest terms? Yes. And I know because there's just a constant 1 on the top, right? It's a -1, but still, it's simplified. There's no way to factor this and reduce anything. So we're good to go. We're looking at vertical asymptotes. The vertical asymptotes are x equals, don't forget that part, otherwise you've got a number, not an equation. These are equations. X equals, and it's anything that makes the denominator 0. 2. That's nice, right? It's almost just like finding domain, except that I didn't have to write the funny interval. Now the second one, I already gave you sort of the end result here. I told you it's not going to actually reduce, but you don't know that looking at it. I wouldn't have known it looking at it. So we try. We try to factor, we try to see what happens. Now this is much like a problem we did in the last section where I've got that negative out in front. I can't just multiply or divide everything by -1, but I can factor the negative out. So that's where we're going to start. If I factor out a negative, I'm left with x squared minus 2x plus 3. And what I really want to know is I really want to know if either of the two parts in the denominator are a factor of what's on top. There's lots of ways I could try to do that, but actually just factoring the top is probably the easiest one. So think about this top and tell me what you think about factoring of this numerator. Okay, so if we did -3 and 1, it would add to the 2 in the middle, the -2 in the middle. But would -3 and 1 multiply to the +3 at the end? It wouldn't. But 3 and 1 are my only choices, right, April? I mean, those are it. I don't have any other choices to put in the ends of a factoring scenario besides that, because this is the number 3. It's prime. So what that tells me is that the numerator just doesn't factor any further. All right? It doesn't factor any further. And because it doesn't factor any further, then that means that the two problem spots from the denominator are in fact asymptotes, because it already is in reduced terms. There isn't any way to cancel or reduce something out. So what are my vertical asymptotes? In this case, there's more than one of them. For this one, x equals 3 and x equals -4, and I am just super excited that both of you said x equals, at least the voices I heard. Got to get that x equals in there, it's very valuable. Okay, so vertical asymptotes, not too complicated. Just looking at denominators equal to 0. At least they're not any more complicated than domain, right? Quite similar. There's another type of asymptote we're going to address next. There is a third one we will address next time, but this is our second one for today, only one for today. It's your horizontal asymptotes. Just write down the first line, okay? I mean, write down horizontal asymptotes in the first line and then pause for me so we can talk about each one of them. Horizontal asymptotes, if the degree of the numerator is greater than the degree of the denominator. That's the first one. If that happens. Then there is no horizontal asymptote. That's all it is. There's just not one. Unfortunately, there is something else going on, and we will have to address this issue later, but it'll be Friday. Okay? So I'd like for you to kind of star this in your notes and to put a note to yourself that says, see example, it's going to be example 6. And we'll talk about more about this case next time. Okay? But it is a flat out true statement. There's no horizontal asymptote. Okay, next one. The degree of the numerator is less than the degree of the denominator. This one is super friendly as well. When this is the case, you do have a horizontal asymptote. It's y equals 0. And that's it. That's just what it is. That's pretty straightforward. You have to decide if you're in the case, but once you're there, you know your asymptote. The last example, or the last case on this slide, says that the degrees are equal. So when the degrees are equal, you do have a horizontal asymptote. And it's harder to write this down, it's more awkward anyway to write this down than to actually do it. Your asymptote is at y equals the ratio of leading coefficients. So I'm gonna almost promise 100% that if you go to lunch today and you tell someone if the degree of the numerator equals the degree of the denominator, the horizontal asymptote is y equals the ratio of leading coefficients, you're gonna sound super cool. Yeah, really smart. Okay, super smart. So let me actually show you how this works with the two examples we've already done, okay? So coming back over here, the first example. Tell me about the degrees of the numerator and the denominator. How are they in comparison to one another? What's the degree of the numerator? Any ideas? That's a good guess, Molly. It's actually 0, though. Because there's no exponent on top, right? There's no, not an exponent, but there's no x to an exponent on top. That's equivalent to having x to the 0 on top, and x to the 0, right, would be the 1 that's there. The degree of the numerator on the first one is 0. What's the degree of the denominator? That's actually 1, because I have an x to the power 1. So which of our 3 cases are we in? The middle one, right? The degree of the numerator is less than the degree of the denominator. So since that's the case, what's my horizontal asymptote? Right. My horizontal asymptote is y equals 0. Done. Determine the case you're in, you've got the answer. Second one. Tell me about the degree of the numerator. What is it? 2. Degree of the denominator. 2. So they're the same, which means we're in case number 3. This is the one I told you it's like awkward to write down. It's not hard to do though, okay? So let's look at what we're doing as it describes it. Well, the degree terms that are the highest are these 2, agreed? And what we want to look at is we want to look at the coefficients in front of them. What's the coefficient of the numerator? -1. And the coefficient of the denominator part? It's 1. So -1 divided by 1. I mean, that's how we find our horizontal asymptote. I'll actually write it out that way. Not that I think you can't divide that, but we got a -1 on top, we got a 1 on bottom. So my horizontal asymptote is actually at y equal -1. Okay? All right, so, I mean, we can find these all day long, but the whole point is to find them for using them to do something. So let's start an example of how they're used. This particular problem asks us to find the asymptotes, intercepts, and then to sketch the graph. So let's start with asymptotes. If I'm finding the asymptotes, we'll start with the vertical ones, just because that's what we've already done before. How do I find vertical asymptotes? It's where the denominator is 0, right? So what do I have to do to that denominator, Addison? Any ideas? Factoring. So let's factor that denominator. How does the denominator here factor? I got the x's. All right, -3 and -2. Does that give me +6 at the end? And does it give me -5x in the middle? Yeah, that's the right one. Good. So knowing that information, we would set each piece equal to 0, right? And my vertical asymptotes would be what?
2 and 3.
Oh dear. Thank you, Julia. Don't forget the x's. X equals 2. X equals 3. And as we're doing this, I'm actually going to sketch the graph so you can see how that plays out on our graph. So we just found that at 2 and 3 we have vertical asymptotes. So how do we draw those? Well, the way that we're going to draw them is we're going to draw them as a dotted line through each of those particular points. So we've got a dotted line through 2, vertical, right, and a dotted line through 3. All right, let's see what else we have. Those are vertical asymptotes. Let's do horizontal asymptote. What's the horizontal asymptote? How do I find it? Maybe I should say that first. We look at the degree of the numerator and denominator. So what's the degree of the numerator? 0. And the denominator? 2. So my horizontal asymptote is y equals 0. Now, I have sort of an unfair advantage that I have colors on my screen. You know, you're welcome to use colors, but do your very best to show me that you've got a dotted line through the x-axis, okay? Okay, the last piece of information for the purposes of this problem's graph that we're asked specifically to find is about intercepts. There are 2 types of intercepts. There's x-intercepts, which is when y equals 0, and then there's y-intercepts. So let's do the x-intercept first. So if y equals 0, in essence I have 0 equals 1 over x squared minus 5x plus 6. A lot of students like to cross multiply to solve something that's in fractional form. what will happen to this if you were to cross multiply? You'd get 0 equals 1. Is that true? No, it's not true. What does that mean? Well, it means that there is no value that makes this work. There's no number that I can plug in that when I take 1 divided by it, I get 0. 1 divided by something is always something. It's never 0. So there are no x-intercepts. Now, if you take a look back at the graph, you might say, well, oh yeah, because there's an asymptote when x is equal to 0. And I'll say that most of the time that's a true statement. We'll come back to it later. For the purposes of this discussion, however, there is an asymptote there, and we aren't crossing the x-axis, so there is no x-intercept. Your y-intercept is easier to find, actually, because I have to let x equal 0. We've been doing that on the last problems and polynomials as well. If x is equal to 0, what do I get for y?
6.
Yeah, I get 1 over 6, right? 1 on top, 6 on the bottom, it's 1/6. Intercepts are always written as ordered pairs, so this is the ordered pair 0, 1/6. And I know the 1/6 is not an easy number to sort of graph on there, and I'm not asking you to be like super duper perfect, but just, it needs to be between 0 and 1, okay? Okay, I'm going to graph one of the 3 pieces of this graph today, and then we're going to stop. We have enough information on the left-hand side of this graph to graph what's going on. It'll look like this. Because if you'll remember what I said, asymptotes are lines that you get really, really close to, but don't touch. So your graph in those pieces, it has to go through the 1/6, but it has to get really, really close to those dotted lines you drew, but not touch them. So it would have to look like this. We'll finish the other 2 pieces of this graph next time.